pretty simple because we're just kind of using really Desmos to explore each of these. So I'm just going to go over to Desmos. Number 1 says, which t-distribution looks more like the normal distribution, one with degrees of freedom of 40 or 1 degrees of 60? So we'll just see how far we have to go with this. All right, so I'm going to type in a normal distribution. 0, mean, standard deviation 1. So this is what the normal distribution looks like. So let's see which one of these would be different. So we have a t-distribution and degrees of freedom of 40. That's the green one. T-distribution. T-I-S-T of 60. All right, so looking at it, everything seems to fall exactly on it. So what I think we could do is we're going to zoom in on the top portion. So this is our normal distribution. Okay, so the blue is the normal. The purple is the 60. The green is the 40. So just by looking at that, I know it's not showing the whole distribution, but I'm just looking at the top. Which one seems to be closest to the blue? The one that has the 60, which is the purple, or the one that has the 40, which is the green? Yeah, the 60. So the higher your degrees of freedom, the closer it approaches to be a normal distribution, okay? And again, you can't really see it if you were just to have this, and the reason I was only looking at the max and not the tails is as your degrees of freedom becomes less and less and less, the flatter and flatter and flatter your curve becomes. So if I, just for all intents and purposes, had a t-distribution in degrees of freedom was 1, I mean, obviously that's very obvious that it's starting to flatten out, okay? And when I say flatten out, look at what the x or the y-axis is. The first main line is 0.2, then 0.4. So we're not growing that much. We've just scaled it to look good. All right. Which t-distribution shows a higher peak in the middle of the bell-shaped curve? Degrees of freedom of 5 or 20? It would have to be 20. The higher degrees of freedom, the better it is. We're on page 113, Finn. Number 3, which t-distribution shows a higher at the far left and right ends degrees of freedom of 20 or 25? Okay, so let's do the degrees of freedom of 20 and degrees of freedom of 25. And it says to the far left and right. All right, so I'm just going to move this over. And remember the blue is the normal distribution. So I'm 3 standard deviations to the right. So the blue is the normal distribution. The green is the 20. And this one says, which t-distribution shows a higher at the far left and far right ends? So I would say the degrees of freedom of 25 is higher. So it's kind of lifting up. It's flattening down, lifting up on the sides. So the lower the degrees of freedom, the higher up it's off the x-axis, is basically what it was saying. Okay, and then show the calculator commands. We don't really have to show the calculator commands on these. I actually can get rid of one of these, and let's just take this down. All right, so what percent of the t-distribution with 9 degrees of freedom? Oops. 9 degrees of freedom, so that's our normal distribution, is greater than 1.15 standard deviation. So I can just do 1.15. And so basically that's 14% of the area underneath the curve with the t-distribution. Number 5, what percent of t-distribution with 20 degrees of freedom? Okay, so I'm just going to change this to 20. And that's going down to 13% because it's getting closer to the area. The curve itself is, because our degrees of freedom is higher, is getting down closer to the x-axis. What percent of normal distribution is greater than 1.15 standard deviations above the mean? Okay, so if I just did this, normal distribution, 0, 1, and we said 1.15. So as you can see, the normal distribution is a little bit less than, you're looking at the same area underneath the curve or the same standard deviation, but the normal distribution has a little bit tighter percent. So the normal distribution shows 12.5% of the area to the right, whereas the degrees of freedom on the t-distribution shows 13.1% or 13.2%. What percent of normal distributions is within two standard deviations from the mean? Okay, so normal distribution, two distributions, or two standard deviations. Oh, that should be -2 and +2. If I do that, that falls into our 95% category. So in this case, it's actually a little bit more, because that 68, 95, 99.7 rule, it's not exact. That's just kind of a foundation baseline. So two standard deviations on a normal is at 95.4%. What percent of t-distribution with 5 degrees of freedom is within two standard deviations? So if I turn this one off and just go to this one, I have 5 degrees of freedom, and they say 2 standard deviations, so -2 to +2. So this one would be 89%. Remember, the other normal distribution was like 95%. So again, this is getting to be a smaller area because the maximum height of our area underneath our bell curve is not quite as tall as a normal distribution. Page 114. It says, assume that a college professor uses a t-distribution to assign grades to each of his students using the degrees of freedom as part of the curve. On the most recent test, he chose 15 degrees of freedom. Show the calculator command. Okay, well, turn that off. 15 degrees of freedom. There's my calculator command. Students who earned a score of more than 2.5 standard deviations above the mean earned an A. So if I went and changed this to 2.5 and went to infinity, so this professor had 1.2% of the students earn an A. What would the percent of A's be increased or decreased if we use degrees of freedom 30? So right now it's 0.12 or 0.012. Whoa. Hey. So if you change that degrees of freedom to 30, so now it's even less people. So now you have only 0.9% would have earned an A. So as my degrees of freedom increases, the area of 2.5 to infinity is less. So there's less A's given in this case. If students scored below 3.5 standard deviations, they would earn an F. So if they scored less than 3.5 standard deviations below the mean, so -3.5. So we're talking about 0.07% of the students would earn an F in this case. And then students between 0.5 and 2.5 earn a C. So between 0.5 and 2.5. So 30% of the students would earn a C in this professor's class. And let's not worry about number 13. Okay, so we're good there. We're good with this. If you were here for these, you're getting the points. If you're not, you have to go through and show me your work. Mikey, Kale, no. Gabby here. Flores here. Lucy here. Winter, you back there? No Winter? Okay. Read. Gabby Jones, Westland, Cats, Kiker. Ethan's back there, right? Yeah, okay. Larkin, in order for you to get the points on this, because we just went over, you got to watch the video and show me tomorrow, okay? Don't watch the video yet because it's not posted. Kale, in order for you to get these points, you have to watch the video. Make sure you do the page 113, 114, okay? Samantha's back there. Okay. Well, my friends, I am on to page something. So I'm on page 43, please. All right. So this is one mean t-test, so one direction. When a hypothesis test is required to using means, we use normal distribution to calculate the p-value. We've done that. We know the population standard deviation in real life. This is rare that we'd actually know what the standard deviation of an entire population would be. We calculate the p-value using the t-distribution when the population standard deviation is unknown, because we must use the sample standard deviation as an estimator of the population of the whole. So we have the group that we can test, a randomly selected group. We can find the mean and standard deviation of that group. We might know the mean of the entire population, but we might not know what the standard deviation is, so we're going to use the mean of the group to apply to everybody. Okay, this process is known as the one mean z-test. Normality is the assumption looks different. This isn't a surprise since the t-distribution is not a normal distribution, even though they appear very similar. For one, a mean z-test is normally, or for the normality assumption is the satisfaction that either the population is known to be normal or the sample size is larger than 30. So there's two different things. So you know the population is normal or we have a sample of 30 or larger. For one mean t-test, the normality assumption is satisfied even when the sample size is very large, as long as the sample is not sharply skewed and has no outliers. This is a judgment call, but it is worth noting that the t-test is very robust. That is, it works very well under conditions that are not ideal with small samples. Okay, so you have your 5 steps. State the null and the alternative. We've done that. Create a null hypothesis sampling distribution. Complete the 7 spots. So we've done that. Calculate the p-value. We've done that. We'll need to convert the sample statistic into a t-score, which is basically we're using a t-distribution of it, and then where it's looking on the x-axis. And then state the conclusion, so fail to reject the null or reject the null, and then check for any assumptions, any red flags, things like that. So on the back page, on page 44, it says, oh boy, this is wishful thinking, my friends. You can tell this was written a while ago. Is the average price of gas in Colorado greater than $2.50 per gallon? Yes. How do I know? I just drove by like 9 gas stations on my way here, and I didn't see anything that was under $3.50, $3.60, $3.70. Okay? So that's my observation. A random sample of 20 gas stations shows an average of $2.54 with a standard deviation of 30 cents using alpha 10. So alpha is going to be our p-value. All right, so we should be able to do this pretty nicely. All right, so the first thing on page 44 is we're going to call mu gas prices. And so our null is gas prices are equal to 250. Our alternative is gas prices the average price of gas in Colorado is greater than 250 per gallon. A random sample 20 stations shows an average of 254. So we want to show that it's greater than 250. So this is directional, so this makes it one tail. Okay. So then we know that our sample standard deviation is 0.30. Okay. It's 30 cents. All right. So we're saying everything, so that would be normal. But then we did a sample of 20 gas stations. Because we don't know the standard deviation of the entire population, but we know it as of the sample, we have to use a t-distribution to make it work. Okay? So we're going to do a t-distribution. We use 20 gas stations. So our degrees of freedom, if we're using 20 gas stations, what's my degrees of freedom then? How much? 19. Yeah, it's one less. Okay? So then we're showing that it's above $2.54. So 2.54 to infinity. Okay, so we have a t-score of 0.00. So we have approximately, let's round that. We'll say that our t-value is approximately 1, because they had said that it was roughly this. So if I change this to a percent, that basically becomes that as a percent. Okay. Now I forgot what I have to do. Calculate the p-value. There's our p-value. I said t-value, I apologize. State the conclusion. And we said they wanted to use an alpha of 0.10. Okay. So let's actually look at this. So I know that 0.0099 is less than 0.10. So we can reject our null hypothesis in this case because we found we found strong evidence that it's away from the mean or away from H naught. Okay, that's basically all we have to do going through it. Was it random sampling? Well, it said a random sample of. We're testing just Colorado, so where we might run into a problem is if they said the cost of gas throughout the United States. We took a random sample of 20 gas stations in Colorado. That's two different things. So that would be a red flag. But in this case, we don't have a red flag because we're testing Colorado. They told us we're testing Colorado, and we're sampling from Colorado. So I don't see any red flags or any assumptions on this. If we reject the null, that means that we could be we reject null, we have a type 1 error. Type 1 error would conclude that We're rejecting the null when the null is actually true. So that's basically what we had to do there. All right. So my friends, I think you have enough to play with. So tomorrow we'll go over page 115, 116, but you have the opportunity to work on it now and get a good start on it. Sound like a deal?